So parametric equations and the parabola. So there's an ingenious way of handling curves by making each coordinate a function of a single variable, okay? Or called a parameter, I should say. So basically, each point on the curve is specified by a single number rather than a pair of coordinates, okay? So like, think of it as if we had like two separate equations, okay, corresponding at the same time, and there was a third variable that represented both of those equations. Now, there's a really cool example that they use in the textbook that we use, and that I'm going to go through that I really like. So think of someone sitting at the cricket, an observer sitting in the crowd, or a cameraman sitting in the crowd. So basically, this cameraman is sitting at a point, so let's say our little guy is out in the field with his bat, okay? Awesome bat, and he hits the ball. And the person who's watching in the crowd, so here's this guy sitting in his seat, watching the person hit the ball, and he watches the person hit the ball, and he hits it this way, such that the observer is directly behind it, okay? So what would the observer see if he was directly behind it? I don't actually know why I drew that picture, but that's okay. What would the observer actually see if he was right behind it? Okay, so he wouldn't see the arc that the ball would actually make. All he would see is just this ball flying up in the air, okay, and then eventually back down. So if we were to graph this over time, okay, basically, we're going to get this sort of, okay, he hits the ball and it goes up in the air, okay, it's up, 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 and at some point it's going to turn back around like that. Okay, so let's say he does that, and someone graphed the equation, and the equation for this was y is equal to, okay, minus 5t squared plus 25t, okay, because the ball is changing its height, so the height we will call y. This person is changing his height, or changing the height, or the ball's changing the height, based on the time, where we can call the time t, okay? So, ball goes up, and it comes back down, and it makes a parabolic arc like that. But let's say that there was a person who was also sitting in the crowd. In a helicopter, or like a cameraman in a helicopter watching like an overview of what happens. So let's say he was looking directly down at this screen, or at this person. So what he sees is he sees the cricket pitch, okay? He sees the person batting, and he sees a ball, and it sees it just getting hit, okay? Because if he's right above it, he can't actually see the arc that this thing makes. All he sees is how far away the ball gets from the batter, okay? So let's say we call the length of the ball, or the distance away from the ball, or the distance ball away from batter, okay? And we're going to call that x, so a variable x, and we'll use this time again, because the further time goes on from where he hits it, the longer and further away it gets. And so what this batsman, or what this cameraman sees, is basically this straight line. The further, or the longer time goes, the further and further this ball gets away. Okay? And so let's say, it's a straight line graph that's further and further away, and let's say it's happening at a constant rate. X is equal to 16t. Okay? So what we can do with these two functions is we can say, okay, well, we've got x is equal to 16t, and y is equal to negative 5t squared plus 25t. Now, the two equations are not directly related. Like, if I was to say to you, okay, let's look at how far the batsman hits the ball away from him versus how high the ball goes in height, okay? There's nothing that directly relates the two, so like, as in, I can't make an equation or write an equation from y is equal to x straight away. What I actually need is to bring in this third variable, or a parameter as we call it. And this parameter t, for time in this case, it doesn't have to be t, but t works well in this case. This parameter t is essentially the idea, or it's the variable that's linking the two, the height and the distance from the person, okay? So as time progresses, the batsman or the ball is getting further away, but it also makes a parabolic arc up and down based on the height. Okay, so with these bits of information, we can actually turn it into an equation, or we can turn it into a graph based on that, based on t. So what we're going to do is we're actually going to draw up a table of values, okay? But this table of values is going to be based on t. So t, and then we've got two equations that we want to fill out, okay? So what we're going to do is going to go 0, 1, 2. We're going to go 2.5, we're going to go 3, we're going to go 4, and we're going to go 5. And it's going to be very obvious why we've put those numbers in very shortly. Okay, so for my x values are very easy. All I'm going to do is substitute some values into there. So 16 times 0, well, that's just equal to 0. 16 times 1 is 16. Okay, 2 is 32. 2.5 makes 40. Then 3 makes 48. 4 would make 64. And 5 is going to make 80. If I could draw these properly, 64 and 80. Okay, so obviously the longer and longer the time goes on, the further and further the ball gets away, and we've decided it's at this constant rate. But the height's going to actually change direction at some point, because we know if it goes back up, it has to come back down. So when the batsman hits it, like as soon as he touches it, okay, well, it hasn't actually gone up anywhere, it's just gone from that position where he's hit it. Okay, and then substituting our t values into our y equation, we're going to get, well, after 1 second, it's equal to 20, and then 30, and then 31 and a quarter, so 31.25, and then 30, so it hits that peak, and it's going to come back down again, okay? So this equation basically, well, these two equations are saying, okay, well, the first one, it's continuing going along, but the second one, it makes this arc type thing, so it's going to go up, and it comes back down. Okay, so we can actually graph these two values against each other with respect to t. So the idea is that we're going to effectively make a graph that's not completely horrible like that. Can we please highlight so I can delete? We're going to make a graph of the x value and the y value together as a pair. Okay, so all my x values are going to go along here, and all my y values are going to go along here. Okay, so you might be saying to yourself, well, how are we going to plot these points? Well, it's quite simple. We're going to essentially plot the points versus the t values, okay? So at t is equal to 0, my first point is 0, 0, okay? So there's a point there, and I'm going to call that t is equal to 0. Then at t is equal to 1, my second point is, so if I call that 20 and that 20, my second point is 16, 20. So it's a bit before the 16, but up at 20. And I'm going to call this t is equal to 1. Okay, my second point is 32, 30. So if I go 40 is here, 40 is here. So my next one is 32, 30. So it's about, halfway and halfway. And this is t is equal to, not 0, t is equal to 2. And we're going to continue this pattern going along. So at 40, it's 31.25. So it's just a bit higher than this other one. So that's t is equal to 3. Okay. And then we're going to put in our 60 and our 80 value. So at t is equal to 4, we've got 64.20. So coming back down. We skipped one. So 48 and 30. Okay, so 48 and 30. So that's about there. And that's t is equal to 4. That's t equal to 3, and this one's t is equal to 2.5, my bad. Okay, then we've got, for 4, we've got 64 and 20, so over at 64, so about there, and 20 again, so that's t is equal to 4. And last but not least, we have t is equal to 5, which is at 80 and 0. Okay, so at each of these time intervals, we've got effectively what is the graph of x, so what's happening to the distance over time, okay? So the distance is getting bigger and bigger and bigger. So as we go this way, the distance is getting bigger and bigger and bigger. So it's getting further and further and further from x, or from x is equal to 0. But then when we go up the y value, we can see our graph goes up and then back down. Okay, so effectively what this is a parametric equation, okay? So this parametric equation is two separate parts. Okay, so these are called the parametric equations of the curve because they're two separate parts that eventually form a parabola. Okay, and I need to stop doing that. So, what we can then do with these two equations, so I'll just write these again. So this is x is equal to, 16t, and y is equal to negative 5t squared, plus 25t. Okay, what we can do with these equations then, so remember we're relating two variables that technically shouldn't be related with a third variable, like with a parameter. Okay, so x and y are both related by t, by the time. Okay, so the time is changing it. But we can actually create an equation for this parabola that we've just drawn above by doing a bit of substituting. So what we can do is we can rearrange t on the left equation, so x is equal to 16t, and that becomes t is equal to 16 on x. And what we can do is we can substitute that into this equation over here, and we'll come up with an equation that is, it's going to tell us what this parabolic arc above us is, what the Cartesian form of this one is. So relating x and y directly. So basically we're essentially removing the time altogether. And then if we're removing the time, we can then work out, if he hit it for 60 meters, or when it gets to 60 meters, how high in the air is it, okay? So remembering this is versing time, but x and y are related in two new ways, okay? So substituting that in, we're going to get y is equal to minus 5 lots of 16 over x, all squared, plus 25 over 16 over x. Okay, so y is equal to, so what we're going to do is we're going to substitute those values in, and we're going to do some rearranging and some multiplying and dividing, and we get minus 5 on 256 x squared plus 25 on 16x, okay? Or in other words, if we put it all under the same denominator, we're going to get y is equal to minus 5 x squared plus 400x, okay, so making the common denominator of 256, okay, because 16 goes into 256, okay, and then factorizing the top, we're going to get minus 5, or we're going to get 5 on the outside, I should say, not minus 5. So we get 5 lots of, 5x actually, because x is common to both, so 5x lots of, 80, which is the 400x divided by 5x, minus x squared. So just rearranging that over 256, and that should be just x, not x squared. Okay, so if we go back and have a look at our initial equation, so back up here, or our parabola, we can see our two roots are at 0 and 80, and our equation over here tells us that quite easily because it's in its factorized form. Okay, and so we go like that. So let's have a look and see what type of examples, oh, this is going crazy. What type of examples you guys would be looking at in this style of exercise, or in these parametric equations. So, we're going to start with example 3 because we're focusing on the quadratic first up. We'll go back then and have a look at linear in a second video, and then third and finally we will look at a circle. So, a parametric equation, x is equal to 2p, y is equal to p squared minus 3, describes a quadratic function. Find its equation in Cartesian form. Okay, so quite simply, we've got x is equal to 2p, so this is part. My drawing tool is not working for me. Having all the problems today. Okay, that's kind of better. Oh. It's new equipment, so it's going to be very interesting first up, I think. Razor. Erase, please. Ooh. Okay. Get rid of this, please. Please get rid of that. Why aren't you getting rid of that? Erase. Oh my god. It's just not doing it for me today. Arrays, please. Okay. That took too long, I think. Okay, so I'm just going to zoom in a bit, and I'm going to try and move my screen up. For some reason, it's not working. Okay, there we go. That's better. Okay, so we've got this question. It says the parametric equation, x is equal to 2p, y is equal to p squared minus 3, describes a quadratic function. Find its equation in Cartesian form. Okay, so what we're going to do is we're essentially going to be finding, essentially doing what we did before in that last little bit. So we're going to be substituting one value into the other to find the Cartesian form. Okay, so we've got x is equal to 2p, and we've got y is equal to p squared minus 3. So what would be ideal is to rearrange the left-hand side for p and then substitute it into the y value there. So x is equal to 2p, well, that becomes p is equal to x on 2. Okay, and then what we're going to do is going to sub into y is equal to p squared minus 3. Okay, so we're going to substitute it into that. And what we come up with is y. Remind me never to do this one again. Y is equal to, so we've got p squared minus 3, so that becomes, so x over 2, go substitute into there, so x over 2 squared minus 3. So y is going to become x squared on 4 minus 3, just like that. So that's our Cartesian equation for that one. So nice and easy. Okay, sketch the graph of x is equal to t plus 1 and y is equal to t squared minus 2t minus 8. Okay, so what we're going to do for that one is we can either make a table of values, or we could just substitute it straight in and get a parabola and then do it that way. That would be the easiest way, I personally think. Okay, so let's start off by writing b. So our two equations are x is equal to t plus 1, so it's a straight line. Okay, and y is equal to t squared minus 2t, okay, minus 8. Now, because this one's pretty straightforward, what we're going to do is we're going to rearrange x. Okay, so rearranging x, let me just calm down a bit. So rearranging x gives us t is equal to x minus 1, and we're going to substitute this into y is equal to t squared minus 2t minus 8. Okay, so substituting that in, we get y is equal to, okay, x minus 1 all squared minus 2 lots of x minus 1 minus 8. Okay, now we're going to expand, so x minus 1 all squared becomes x squared minus 2x plus 1 minus 2x plus 2 minus 8. Okay, now we're going to simplify, so we're going to get x squared, since there's no other x squared terms. Minus 2x is minus 4x. Okay, 1 plus 2 is 3, minus 8 is negative 5. Okay, so this is the equation, or the Cartesian equation, for our two parametric equations. I don't want you, I want to do you. Okay, now our next step is to graph this thing. So when we are graphing this thing, okay, we're going to need some intercepts. So x-intercepts and y-intercepts, and that should do it. So for x-intercepts, let y be equal to 0. Okay, so we get 0 is equal to x squared minus 4x minus 5. Okay, two numbers that add to negative 5, add to negative 4, but multiply to give negative 5. Multiply to negative 5, add to give negative 4. I'm going to go x minus 5 and x plus 1. Okay, so therefore the x intercepts are x is equal to 5, because that's what makes it 0, or x is equal to -1. Okay, for y-intercepts. So for y-intercepts, let x be equal to 0. Okay, so this is the easy one. So we get y is equal to 0 squared minus 4 lots of 0 minus 5. So the y-intercept is y is equal to -5, just like this. Okay, so now we've got enough information to be able to draw this thing. Didn't want that. So let's draw this big boy. So Cartesian plane, like so. Now we know our intercepts are at x is equal to -5. Oh, sorry, y is equal to -5. And we've got some values at -1, and we've also got one at 5 as well. Okay, that -5 could actually be quite a bit lower, so let's put it down there. Okay, the other thing that we probably need is our turning point, if anything. Our turning point is at about, it's halfway between -1 and 5, so that's at 2. Okay, so it's somewhere down here, and it's going to be somewhere down here. Okay, we're not too overly cautious about that at the moment. So drawing it, it's going to go through there, it's going to go through there like that. And hopefully yours looks a lot better than mine. It's very hard to draw on this thing. But basically, it needs to go through this point here, and that point there. Okay, and that's the equation. Okay, part C. So we're going to have to go back up and have a read of part C. So part C says, write the quadratic function y is equal to x squared plus x minus 1 in parametric form using x is equal to 2m minus 2. Okay, so for one like this, okay, let's scroll down. Put my pen back on. Okay, so we've got x is equal to, and I should write C here, x is equal to 2m minus 2. Okay, so what we're going to do is we're just going to substitute that straight in. So substitute into the Cartesian equation. Okay, so that is y is equal to, okay, so we've got 2m minus 2 squared for the x squared bit, plus 3 lots of 2m minus 2 for the 3x part, and then the minus 1 for the minus 1 at the end. Okay, so y is equal to, so just expanding, we get 4m squared minus 8m plus 4 plus 6m minus 6 minus 1. Okay, so putting it all together, we get 4m squared, okay, minus 2m minus 7 plus 4, so that should be minus 3. Okay, so 4m squared minus 2m minus 4. So the equations in parametric form. So the equations in parametric form is, well, that should say are, x is equal to 2m minus 2, and y is equal to 4m squared minus 2m minus 3. Okay, so that's pretty much it for that one. Okay, I'll catch you guys in the next video where we talk about, or we do some examples of linear ones, and then we will have a look at these circles.